In this video, we will now apply the method of Lagrange multipliers to Lagrangian mechanics. And as we'll see in a minute, that will actually allow us to find the forces of constraint that we previously were not able to access. So let's say now that we have an action that corresponds to this Lagrangian, which depends on the position in x and y of some particle. Okay. And as we've done several times already, we're going to introduce paths that are variations on the correct solution. So we'll say that capital X of t is little x of t plus the variation on x, which is also a function of t, and the same thing in y. And as we've done before, we know that S is stationary if delta S, which we define as S at capital X and capital Y at those two paths, minus the action at the correct paths. That's going to be something on the order of the variations squared. Okay, so delta S then we can show with a little bit of work, and we have done this already, so I'm not going to go through it, but we can show that this becomes this. So that's just a chain rule, although it's applied to these variations instead of to normal differentials, but it works just the same because there are small deviations away from the correct path, as you've seen a number of times before. And then we could group the terms in x and y together. Well, first of all, what we're going to do is we're going to integrate the second term here and the fourth term by parts. And as you've seen, I think 3 times already, this gives us the following. Like that. The only thing that's different from what we've done previously is the notation. We used something like eta and psi times of the constant last time. But otherwise, everything is the same. This is supposed, well, and then in principle there's something here on the order of delta x squared. But if we ignore that, which we can if it's small enough, then we can say that this has to equal to 0. And that gives us the 2 Lagrange equations. As by the fundamental lemma of calculus of variations, each of these integration arguments have to be independently equal to 0, because we can choose delta x and delta y any way we like, as long as they vanish at the endpoints t1 and t2, as we've seen several times already. Now, so far so good, but what we're going to do now is we're going to introduce a constraint. G of x and y equals some constant. Now, previously what we've done in this case is we just use this relationship to replace y with x and then get rid of x or y altogether in the definition of the Lagrangian, and then we can do the same thing again, and then we just get a single Lagrange equation. But what we're going to do now is somewhat different. And that's going to make use of the idea of Lagrange multipliers. So the way this basically works is that delta x and delta y are not independent. So it means if I take this constraint here and define delta g as g of capital X and capital Y minus g of little x and little y, then we can use the chain rule, just like we did over here. But now, because delta x and delta y have to satisfy the constraint, both this function here is equal to a, and that function too is equal to a. It doesn't matter which path we're following, we are obeying the constraint. Since we are obeying the constraint, then this is equal to 0. This means that we can use this. We can take this quantity and we can multiply it by some function lambda of t, and then just add it up here. It's not going to change anything because the delta g is 0 anyway. So we're going to now write down that delta s is delta s plus some lambda of t times delta g. And as you can see, one of these terms here depends on x and the other one on y. So it's natural to group them with the particular part of delta s that depends on x and y. So what we get is this. Now, lambda of t is actually any continuous function. So we can choose that, in principle, to make the first integral equal to 0. Right. So this is equal to 0 by our choice of lambda of t. And since the entire expression here, delta x, has to equal to 0, or at least it's no bigger than something on the order of delta x squared and delta y squared, that means that this equation too is equal to 0. So what we are left with then are the new Lagrange equations that incorporate this Lagrange multiplier function. So instead of using now the constraint to reduce the number of variables, generalized coordinates, from 2 to 1, we have used this Lagrange multiplier method, because lambda here is a Lagrange multiplier, to keep two different, in principle independent, Lagrange equations. And to them we also have to add our actual constraint. So then we are left in a situation where we now have 3 equations, which will give us 3 functions, x of t, y of t, as well as lambda of t. Now this is of course much more complicated than just substituting to get rid of either x or y. Then you would have had only one of these. Now you have 3 separate things that you have to work with. So you only do this when you have to, when what you really are after is the forces of constraint. So let's now show how this actually helps us find the forces of constraint. We know that we have Newton's second law, which says that the total force equals ma. But the total force, as it turns out here, is equal to the non-constraint force. Let's make this vectors. The total force is the non-constraint force plus the constraint force. And for the Lagrangian method to work, we know we are able to write this force, the non-constraint force, as the gradient of a potential. So that's minus delta u, minus gradient of u. But as far as the constraint force is concerned, that's not necessarily possible, so we have to keep it this way. Okay. So Newton's second law now says that the total force is d to t of p. And we know that we can write this force, and this is in vector form. We can write that, of course, as vector components. And then we can use the fact that we know that the total force is the derivative of the Lagrangian with respect to the ith generalized coordinate here. This is the L, the xi. That will give us this part here. Right, the L, the xi is minus du dxi, right? Because the Lagrangian again equals the kinetic energy, which depends only on velocities in principle, and then minus the potential. So this is minus the u dx, and then we have to keep the constraint force. And that's now equal to d dt of d Lagrangian dxi dot. So if you compare this equation here with this equation up here, we can immediately identify that the ith component here of the constraint force is just lambda of t times the partial derivative of the constraint with respect to xi. So that's the other result that we have. So these are the new Lagrange equations in the presence of a constraint, but we're not using the constraint to reduce the number of dependent variables. We're using it to define a Lagrange multiplier, and from that Lagrange multiplier and the constraint, we can directly find the forces of constraint. And that's why you would do this. Comes at considerable cost, as you can see. This now becomes equally complicated as actually applying Newton's second law directly. But it still has its advantages because this form is still independent of coordinate system. You still don't have to think about what type of coordinate system you have in order to write this down. So let's apply this to one simple example. And that is the case of the Atwood machine. That's what the Atwood machine looks like. And the way we define things is that we have generalized coordinates x and y, which are the distance of each of these two weights downward from this dotted line, or this dashed line. There is, of course, a constraint here that is set by the length of the string. But we're now going to use the method of Lagrange's equations, of Lagrange multipliers, in order to figure out what the actual force here is in the string, the tension force, which you weren't able to do previously with the regular Lagrangian approach. So our goal here is to use Lagrange multipliers to find the tension in the wire. So the first thing we do is we write down the Lagrangian without any constraints. Lagrangian without constraints is simply 1/2 mx dot squared plus 1/2 m1 x dot squared plus 1/2 m2 y dot squared. And this is minus the potential over there. So that's the Lagrangian. And then we have to separately introduce the constraint, which is just that x plus y have to be a constant, right? So we take this length plus that length, that's always going to be the same. And that constant I'm calling L in this case. So now let's write down the Lagrange equations with the Lagrange multipliers. Since we haven't gotten rid of any generalized coordinates, there are still two of those. Right, so now we just have to apply all these things here. So the L dx, that's just m1g. And then we have lambda, the g dx, that's just 1. And then we have d dt acting on the L dx dot. The L dx dot is just m1 x dot, right? So that's m1x double dot. And the same thing happens here in y. We get m2g, that's this term, plus lambda times the g dy, that's also equal to 1. And that is equal to m2 y double dot. All right. Now if we look carefully here at the constraint, we can see that it gives us that x double dot plus y double dot equals 0, or in other words, x double dot equals minus y double dot. That means we can use this to eliminate lambda from these equations, right? Because we have x double dot is a function of y double dot. So let's do that. And I'm going to do that by just taking these two equations. I'm going to call this one equation 1, and I'm going to call that one equation 2. So equation 1 minus equation 2. But using this now, you have this, And we obtain and that's the same result that we obtained earlier when we solved this using the regular Lagrange approach. The advantage here now is that we can get the tension force. Tension is going to be lambda times the g dx, for instance. So that's just lambda. And we can see immediately what lambda equals here. That's from, let's say, the first equation here. So it's equal to m1 x double dot minus g. But x double dot we found over there. So this is therefore just equal to and that's a tension, which we're able to find because of the Lagrange multipliers. We can see that that is a reasonable force if the two tensions. Oh, there's a minus sign in front of here too. That needs to be mentioned. That if the two tensions are equal, if the two masses are equal, then the tension will just be mg. In the strings here, just like what you'd expect. And the minus sign here, in case you're wondering, is coming from the fact that x and y are downwards. The tension is actually upwards. It's in the opposite direction of the coordinate directions. So the tension is there. So you can see the tension is in the minus x direction or in the minus y direction. So this is the method of Lagrange multipliers applied to Lagrangian problems in order to find out what the forces of constraint are. And that's when they're useful. If you don't need to know the forces of constraint, you should not use this method because, as you can see, it is more complicated than just simply taking the constraint and using it to reduce the number of generalized coordinates that you are working with.